Okay, I'd like to introduce Dan Gaffel. He's going to talk about ecological hazard assessment of potential impacts to fish from emerging contaminants.
Good afternoon, everyone. Thank you for being here. Yes, my name is Dan Gaffel. I'm with the U.S. Fish and Wildlife Service in the New York field office. I'd like to thank my co-authors, and I'd also like to thank the conference organizers. The contents of this presentation are based on this document, which will be published soon. This presentation is organized according to the classic ecological hazard assessment framework. This is the outline of today's talk. The overall goal of this assessment is to identify relative hazard to fish populations due to CEC exposures among sampled areas and among the CECs themselves. There are classic elements that I'm going to include in the problem formulation step. The ecological receptors are fish populations not limited by species and therefore not limited by range of sensitivity. The principal exposure pathway is direct uptake from water. The temporal scope includes a 5-year sampling period where the sampling events were variable in terms of the season and the time of day collected. The ecological scope includes both lentic and lotic systems, large and small. And although we're all interested in the universe of potential effects from CECs, in practice, this assessment was limited to 14 CECs for which we derived screening values. The geographic scope spanned 6 Great Lakes states. There were approximately 200 sampling sites distributed among 24 project locations. The toxicity assessment, I'm going to be brief because it's expounded on in detail in other places. The goal of the toxicity assessment is to develop defensible screening values for CECs in water that we can use to distinguish between sites and between CECs with respect to the potential hazard to fish populations. We've completed that goal and we've fully documented it, and this publication is due to enter the publication pipeline very shortly. For your sake, I'm going to define a couple of terms here which will be useful in the rest of the presentation. We derived 2 different types of screening values. SV lows, which are concentrations in water below which we do not expect to see significant adverse impacts, and SV highs, which are concentrations above which it's reasonable to expect adverse impacts. We had 3 principal outputs from the toxicity assessment. There were pairs of SV high and SV low final values for 14 CECs, and these screening values incorporated information from a range of effect categories. There were also effect-specific SV high and SV low values, and those highlighted the information from within effect categories. So, for instance, reproductive effects and developmental effects. And then we also have derived distributions of both SV highs and SV lows, and currently we're exploring whether they can be useful for distribution-based hazard assessment. If you want more detail on the toxicity assessment, please stop by the posters in this evening's session. I'd be happy to talk with you. The exposure assessment also contained familiar elements to it. I'd like to call out a thank you to the USGS who were instrumental in coordinating and conducting the water sampling, and they performed all the analyses for all of the water samples that were included in this assessment for a number of CECs. Again, though, we focused our assessment on these 14 because these are the ones that we derive screening values for. But as luck would have it, they span a pretty interesting diversity of human uses. So our exposure assessment is comprised of a number of sampling events that fit into this matrix. And so we have approximately 500 data points per CEC, maybe a little bit more than that. And in some cases, we did a conversion from unfiltered CECs to aqueous. And the reason for that was because we wanted to be able to compare the aqueous CEC concentrations against our screening values. And so we come to the hazard characterization. And that is the familiar paradigm where we compare the exposure information against the toxicity information. And in our case, we developed hazard scores to address our objectives. And I'd like to start out with an example of how to apply the pair of screening values. Let's suppose that we have this distribution of estrone maximum concentrations in water. And each element of the distribution represents the maximum concentration in one site. And so we can assign all the sites with concentrations, maximum concentrations below the SV low, a value of 1. And all the sites with maximum concentrations above the SV high, we can score with a value of 3, and everything in between, a value of 2. And so each site gets 1 hazard score. In the Great Lakes work that we did, first what we did was we scored each sampling event. And then by averaging those by site, we came up with 1 value per site, per CEC. And when you arrange those scores in this array, what we find is that if we take the marginal averages for the CECs across sites, we can rank those averages with respect to relative hazard to fish populations. And similarly, we can do the same with ranking sites. If we group the information from the sites within a location by taking their mean, we can come up with a location-specific hazard score. And so we can then order our project locations with respect to relative hazard to fish populations. The red shaded ones at the top are the most hazardous, and the green shaded ones at the bottom are the least. If we rearrange the locations geographically, west to east, from top to bottom in the left-hand column of this table, we retain the overall scores that we just saw in the last slide, but I've added to this slide the effect-specific scores as well. And what we see is that certain locations they come out as being the most hazardous from among all the rest. And it's confirmed by looking at various effect categories. We can do a similar scoring and ordering of the hazard scores by CEC. And what we see here are some interesting things. In the behavioral effect category, the 2 antidepressants are the ones that have the most hazard associated with them. And ibuprofen has a more diverse set of high hazard scores than any of the other CECs. When mapped across the basin, what these results essentially comprise are a composite prediction of relative hazard to fish populations among the project locations. If we focus this method on fewer project locations, though, we can zoom into a finer spatial scale. And the next few slides are going to show an application of the river reach spatial scale by applying the hazard scoring and ranking across these sites. In this way, we've predicted that the Cuyahoga River sites are the most impacted relative to fish populations overall. When we also consider effect-specific relative hazard, the Cuyahoga River remains the most impacted, but this site is identified as consistently high scoring among all the effect categories. This site is associated with a wastewater treatment plant, as are these two Racket River sites. And we don't see those as having been impacted until we look at effect-specific category scores. And in this case, it's reproductive hazard associated with those two. And also the Fox River site here. So what these comprise are essentially a prediction of relative hazard at these sites. And we're interested, though, in how well do these predictions hold up when they're compared against real-life data. And so we want to know what the degree of correspondence is between the predicted and the observed. And our validation approach was essentially qualitative at this point. So we looked at data collected or reported by Jorgensen et al. In a paper recently submitted, and they looked at an array of effect endpoints at these same locations. I went ahead and categorized those effect endpoints according to the same effect categories that we used in the same process that we used when we developed the hazard, the screening values for hazard scoring. And let's focus on reproductive because there's the greatest number of endpoints in this data set. And when we lay those out next to each other, so the hazard scoring that I showed earlier is in these two columns, and Jorgensen et al. Effect ranking is in those other columns by fish species. And again, we see a correspondence between the predicted based on hazard scoring and what Jorgensen et al. Found in their own data set in terms of relative hazard. And the same site where we identified as the most consistently impacted across effect categories, Jorgensen et al. Identified as the most impacted site in their assessment of the empirical data. And there are differences in species sensitivity, as you see in the data set from Jorgensen et al. If we group the information, however, by sex, we get a similar pattern of spatial correspondence between predicted and empirical. Interestingly, the degree of correspondence, though, appears sensitive to the type of measured effect endpoint. If we focus on validation on plasma chemistry endpoints relevant to reproduction, whether it's grouped by species or by sex, we find a poor correspondence spatially with what we predict versus what is found in the field. However, at the organ level of organization of effects, we see that the spatial correspondence is there. Again, whether we group by species or by sex. So in summary, we've illustrated that the screening values are useful for illustrating relative hazard across various spatial scales. We've identified specific relatively high hazard project locations and CECs, and the preliminary validation is encouraging. The next steps include to complete the hazard assessment document and make it available, to expand the validation process, and to explore the potential for a distribution-based hazard assessment. And I'd like to add one more, and that is to add to the list of chemicals for which we've developed screening values. And that's it. Oh, no, one more point. I thank everybody on this slide. Again, a huge effort. Many different people contributed. I'd like specifically to call out the Great Lakes Restoration Initiative. There's the funding stream through which this project was funded, and also the project management in the Fish and Wildlife Service, who are located right here in Bloomington, without whom this project would not have happened. Thank you.